That's fine. All right. Good morning, everyone. Welcome back to Math 161 in our 11th week, I think, the end of the 11th week. Maybe the first class of the 11th week since we missed one day. That's right. Either way, not the most important aspect in the world. Deep sigh, because as you can see highlighted at the top, my math lab has still been acting like a terrible 2-year-old. I don't know what's going on with it. It was much worse Monday and Tuesday. By Tuesday night at like 10 o'clock, it seemed like everything was fine. But then Wednesday, when I started going in trying to do partial credit for people's tests between my classes, well, I wasn't able to do anything, unfortunately. I couldn't even get into my shells. Before I could get into the shells and everything was just working slow, blah, blah, blah. Point is, I can't expect to give you rigid due dates and deadlines and things when this is going on. I know that most of you have managed to take the test at this point, but I do know that I have some of you that have emailed me and said it was messing up, or I'm just going to assume because I've seen you doing your other homeworks and you haven't taken a test yet. So I'm trying to give benefits of the doubts if you haven't checked in with me. And to those of you who have emailed me and have been waiting for an individual response, you're probably not going to get it, except unless it was about the partial credit. But if it's something else, my inbox was just completely flooded, and that's a good thing because y'all are supposed to be communicating with me, but it just got to the point where it was going to be impossible to respond to every single individual message. So if you don't hear back from me on a partial credit a partial credit request, by tomorrow afternoon, check your test scores, see if they've been updated. If they haven't, then maybe just reply to that email that you already sent to me and say, hey, Mr. Beckner, what's the status on this? And it could be that my math lab is still acting up. It could be I didn't get a chance, but my plans for today when this class is done is to spend about 3 hours across all my classes just getting my math lab stuff together because I haven't been able to do anything. I did get in long enough this morning to update these due dates. You can see that 2.7, 2.8, and test 2, because my math lab has been acting this and they had due dates in that window, have all been extended to April 2nd, tomorrow. This is not an April Fool's joke. So as long as my math lab keeps behaving, we're going to stick to those dates. But if I go in there and I see that it's acting up again and my students are emailing me saying it's acting up, then I'll extend as needed. So again, these 2.7 and 2.8 due dates, not really accurate anymore. I did have a chance to update those. You know, the only class I've been able to update due dates on. My other classes, it wouldn't let me in last night. 3.1, we finished last time, and then 3.2 we will finish today. So those due dates are a week from when they were finished per usual. Again, the test 2, I left the old details up here, but you can see in the highlighted section that it's actually due on the 2nd. If you took the test and it wasn't letting you progress through questions, like you were only able to see 10 or 11 questions the whole time, and I can tell this when I go in, I can see that you never accessed a question and didn't have a chance to do it. I can give you a second attempt, but you need to email me individually. Make sure you say pre-calc 1 test 2 in the email title, and please understand that if you do get a second attempt under these very, very extenuating circumstances, test 1 is completely out the window. If for some reason you do worse on test 2, that will be your grade. Sorry, I had a cough and that was a big one. Didn't want that mic'd. So if if you thought you had a sketchy situation, but you got a B on test 2, I don't know that I would take the reattempt just to be safe, because you don't want to go from a B to a C or a B to a D because you weren't prepared or something like that, or you were just trying to, maybe wiggle your way through something. I don't know. But anyways, I know I had to talk a lot about this morning, but just please understand that when it comes to technical limitations, I'm very understanding with this stuff. And hopefully this will be the only time my math lab has issues, but of course it has issues when every single one of my classes are taking tests. So this has been fun. You just got to laugh at these situations. Please don't be stressed at them. Again, I'm not gonna let these issues cause chaos in your life. All right, so that being said, let's pick up right where we left off in 3.2 with no further waiting.
So continuing where we left off last class, talking about graphing polynomials. So we spent most of last class talking about graphing quadratics, graphing parabolas, the vertex, the intercepts, all that stuff. We did lots of examples. Please go back and watch that lecture if you haven't already, or if you need more time with it. Now we're going to go to the next degree up, or the next degree up, or even 10 or 12 or 50 degrees up. So instead of just allowing x squared, now we're going to have x to the third, x to the fourth, x to the fifth, x to the whatever number as long as it's whole. And we said we're going to need several things. We're going to need to get our ducks in a row, just like with graphing quadratics. But these things are going to be a little different. Some of them will relate to it, like we'll want maybe some intercepts. That would be really good to have. But there's a lot more curves. There's a lot more bending to these. So we need to know, well, first of all, what happens as you go towards your infinities? What happens as you go towards negative infinity in the x direction and positive infinity in the x direction? And that's what we're talking about, whether the function goes up or down. So we have this, what we call the leading coefficient test to determine the end behavior. The leading coefficient test to determine the end behavior. We talked about if the leading term, which is the term that has the largest exponent, if the exponent's even, they both point up or down based on whether that leading coefficient is positive or negative. And we said if the leading term's exponent is odd, they point in opposite directions. The left goes down and the right goes up if the leading coefficient's positive, and vice versa if negative. And I said that while you can flat out memorize that, it heavily relates to the graphs of x squared and x cubed, what happens on their outsides. So we said this is basically the same thing, it's just when you ignore all the stuff in the middle of them, these four images 100% correlate to what we see above. And it wouldn't matter if this was an x to the second, x to the fourth, x to the sixth, x to the eighth. It doesn't matter what happens in the middle. Those ends would both go up or both go down based on whether that number is positive or negative. I also pointed out that we're going to come back to the graphs of x squared and x cubed to talk about something else in this section. So if you don't have these shapes memorized, it would not benefit you, to say the least. The last thing I want to point out, and this will be relevant in one of the examples that we do, is that sometimes you're given a polynomial in a factored form. So instead of looking like x to the fifth plus 7x squared plus 3x minus 7, I don't know. So that's a non-factored form. So you can tell what your leading term is already. Sometimes these things are given to you in a factored form. So it might look something more like, I don't know, 2 parentheses x minus 3 parentheses x plus 4 squared parentheses x minus 1 cubed, da 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 da. So when it looks like this right version, that's what I'm talking about here. So if your polynomial is factored, just consider the sum of the exponents of each factor, and then the leading coefficient is still just the number in front. So that's basically us pretending to multiply everything out, but only multiplying out the first term of each. Trust me, it would be 1,000 times more work to actually multiply or FOIL this middle thing, FOIL the cube, then multiply it by the third one, then multiply it by the middle thing, then by the x minus 3. I mean, that's literally a 20-minute problem, probably for someone who's really good at math. Someone who hasn't done it for 30 minutes, 35 minutes, I don't know, but it's going to take more time. But we don't need any of that. Basically, all you do is you just pretend the numbers inside of the parentheses aren't there, and it's like having a 2 times an x squared times an x cubed, and then that is essentially your leading term. That's what I'm referring to with this note right here. And again, that will come up, so keep it at your disposal. All right, how do I want to do this? How do I want to, that does take up a lot of space, so I'm just gonna have to go down here. Example 1, determine behavior of the function. And for A, go ahead. Lots of space, lots of space. And this is going to be f of x equals 13x to the 6th minus 4x to the 3rd plus 21x squared minus 11. So that's our problem. And all we need to do is say, hey, the leading term is the 13x to the 6th. That's all we care about. For the end behavior, I don't care about any of this other jazz. And you might say, oh, well, because it was the first term, right, Mr. Beckner? No, because it was the term that had the biggest exponent, which is not always going to be the first term. Spoiler alerts. All right, so that's our leading term. I don't want this circle to stay there. Now remember, this whole idea is based on whether the exponent of this is even or odd. So the exponent here is even because it's a 6, and the leading coefficient of 13 is positive. So it's got a positive coefficient. So here's the way I do it. I don't go back to just that a little blanket if this, then that, if this, then that. Like I said, I just think about what do graphs of x squared and x cubed look like with positives or negatives. So an even exponent with a positive coefficient, that relates to the x squared graph, the positive x squared that is. But again, we don't actually know any of the stuff in the middle. We just know that the ends are going to go up. That's how I do that in my head. If you want to do the blanket memorization, you go for it. So here's a couple of different ways you could answer this. You can actually draw a graph with just a missing middle section. This is what I like to do by hand. And then just on the outsides of it, point both ends up. That's an answer. You could also informally say both ends point up, but I don't really like that. I would use something that goes a little more in line with interval notation, but not actually in the interval notation. So this is called arrow notation. So as x points at negative infinity, this means goes to. So the arrow means go to. In other words, as x goes left forever. This is left forever and ever and ever. We're going left all the way out to negative infinity. So as we go left forever, what does the graph do vertically? The y value, it's going up towards positive infinity. This just says as x goes left, y goes up. As x goes left, y goes up. Sorry for the ugly goes. That's all that says. As x goes left, y goes up. Or as your graph goes left, it goes up as well. That's another thing, another way of saying it. So that's left and up. Now we got to talk about the right side. We'd say as x goes right forever, which is to positive infinity, the y value also goes up. So the infinities for the x's mean left or right. For the y's, they mean up or down. You have to be careful. You have to pay attention. There's a lot of ways that you can mess that answer up, obviously. But there's also a lot of ways to get it right. Now, my math lab, I believe, does the arrow notation. But again, if for any kind of handwritten component for showing your work, you could have this as well. Now, if my math lab's only taking this arrow notation, you do have to learn the formats of those answers. That's something I could give partial credit on a test for. But even if this is correct, if you have this wrong, I would not give you full credit because I'm telling you, you have to learn both notations. When you go to calculus, the arrow notation is quite honestly much more important. I like this left version because this just kind of helps us set up the graph. It's a better visual image. All right, for B, let's do f of x equals 3x minus 20x to the 9th. So a lot of people will say, oh, okay, well, here's our leading term. It's the first term. There's no exponent written, and some people might get freaked out by that, but that means it's a 1. But guess what? That's not the leading term. This is the leading term, because that's the thing that has the biggest exponent. And yes, I did mean to circle the negative in front of the 20, because that negative will tell us which way the ends will ultimately point. All right, so the leading term is the negative 20x to the 9th, which means the exponent is odd, and it's a negative coefficient. So that relates most of all to the x to the 3rd graph, but not the positive x cubed, the negative x cubed. Positive x cubed In red, I'm doing the positive x cubed, would look like this. That I've told you to memorize many times, but that's got a negative in front, which is a vertical reflection, which means the negative x cubed graph looks like this. Now again, with the extra terms, the higher exponents, we honestly have no idea what happens in this middle section. So we just cut it out. But we do know the ends make that shape. So for our picture, which again will be very much more helpful for us graphing later. No clue here, but the left goes up and the right goes down. Or more formally said, as we go left forever, which means as x goes to negative infinity, that's left, the y value goes up to positive infinity. Left, up, left, up. Conversely, as x goes right forever and ever and ever, we can at least say that y is going down to negative infinity. I'm not talking about how fast it's doing this. I'm just saying that ultimately it does that. All right. C, f of x equals -3 parentheses x minus 2 squared times x plus 5 to the third times x minus 1. Now, before I do this, I want to point out that, hey, this leading coefficient was an even number that had nothing to do with whether it points up or down. The even or oddness of the coefficient does not matter. We don't care about that. All we care about is whether it's a positive or negative number. We care about the even or oddness of the exponent. So you got to keep those ducks in a row, so to say. All right. This is what I was alluding to earlier. This is in a factored form. You do not want to multiply that out. It's not worth your time and effort. What do? Just consider the sum of the exponents of each factor. So once again, you're basically just ignoring the plus a number or minus a number inside of all these parentheses. So what I like to do is I like to say that this function is approximately, and this is only true for really big values of x in absolute. So I'm talking about x equals 1,000 or 1,000,000 or 1,000,000,000. Basically, we can just ignore all the pluses and minuses inside, and it's -3 times x squared times x to the third times x to the first. And I'll write the 1 for clarification. That's where that 1 came from. 2 plus 3 plus 1 is 6, so this is -3x to the sixth. This is the leading term of that polynomial. And when your x is ridiculously large, the x to the thirds, the x to the fourths, the x to the fifths, they are minuscule in comparison to what this term is doing. So this term is just basically taking the wheel. It's taking over. So our leading exponent is, our leading term's exponent is even. So it's an even exponent with a negative coefficient. That's all we need. So we know it relates to an x squared graph, but it's going to be the negative x squared graph, which would point down. Now, once again, we have no clue what happens in the middle region for small values of x in absolute. We just know that the ends go down, left and down and right and down. So that is not me memorizing the if this then that, if this then that case. That's me trying to relate one thing to another. So if you want the picture, middle space of unknown, but the left and the right ends both point down. I'm not saying they start at a height of 0 and point down. That's very obviously not the case in general. I'm just saying that ultimately the ends point down. So then we can say as we go left forever, as x goes to negative infinity, the y value, you could even write f of x here instead of y. Remember, those are interchangeable. The y goes down to negative infinity. And as x goes right forever to positive infinity, the y goes up. Right? Inflection and voice? No. It goes down as well to negative infinity. Don't try and overanalyze this negative, positive for the infinity stuff. Remember, negative infinity and positive infinity are left and right for x's. For y's, they're up and down. That's all you need to think about. That's all you have to consider. So that is the end behavior test. That's how we know what happens for the extreme values of your inputs, your x's. But what about this whole middle section? I mean, for real, what really happens in here? Well, we got to start working on that. And the first thing we should do is find the zeros, which is just another name for x-intercepts. So zeros, also roots. Roots is another word. Zeros, roots, x-intercepts are all literally the same thing, and you'll hear different math teachers use different words. I like to use all three just to keep everybody up to, up to par. This end behavior stuff, let's not worry about that yet. Not end behavior. I don't know why I said end behavior. The multiplicities. So the zeros of a polynomial are found by setting the function equal to 0. Literally the same thing as finding the x-intercepts. Literally the same thing we were doing back in chapter 3.1, section 3. So that means we can go straight to an example. Example 2, find all. And I like to underline the word all for this problem. Find all zeros of the polynomial. And for a, we're going to do f of x equals x cubed minus 2x squared plus 4x minus 8. Now, when I say finding zeros, we're going to be solving equations that are quadratic or higher, which means factoring may come into play. The quadratic formula may come into play, or completing the square if you prefer. The square root property of taking a plus or minus square root could come into play. All of those techniques for solving equations that we've gone over, which you were technically supposed to know before this class began, are all on the table, which is why I've specifically started out with one that a lot of people might have forgotten how to factor. There are 4 terms here, and whenever you need to factor something with 4 terms, in this course, I've said you factor it by grouping. Before we get there, let's actually show the work of finding the zeros, which is where we set the function equal to 0. So we just go 0 equals x cubed minus 2x squared plus 4x minus 8. You could have put the equals 0 on the right. Nobody cares which side it's on. Now we factor, and we factor by FBG, factor by grouping. 4 terms, factor by grouping in this course. Again, in the real world, not a guarantee, but in here, I do guarantee that. So that's where we do a GCF for the first pair, then we do a GCF for the second pair, and we hope that the parentheses match, and then that's our third GCF. So our first GCF would be x squared. We can take an x squared from both of these terms. They both have x squared in them. So then we open our parentheses. X cubed divided by x squared is x, minus 2x squared divided by x squared is 2. Then we take a GCF from the second pair, but remember, you might need to take a sign. So this is a reminder for that special hint I gave you and a reminder that things never go away. This sign, like 99% of the time, is what you put next. So if that was a minus, we'd be factoring out a negative. So plus, between 4x and 8, the GCF is 4. Then we open a parentheses, 4x divided by 4 is x. I was about to say 4 on accident. If this was a negative 4 here, we'd be doing 4x divided by negative 4, but that's not the case. Then negative 8 divided by 4 is negative 2. And look at this. We have a third GCF of x minus 2. It's here and here. It's being multiplied here and here, which means it's a common factor. So what we do is we take that GCF out, and I usually like to do the new stuff in the red color. I'm actually going to do blue because it's already in blue. So what do? We write the GCF first, just like before. You open a parentheses, and then technically you're supposed to divide each of these terms by the GCF. But I gave you a hint previously, and I said if you just cover up the GCFs in each term, that's exactly what goes in the next parentheses. So the next parentheses would be x squared plus 4. That's it. Now, x squared plus 4 is not factorable. So if this was x squared minus 4, we'd go x plus 2 times x minus 2. It would be a difference of squares. This is a sum of squares, which is not factorable, asterisks, using real numbers. I will finally stop lying to you about that eventually, but for now I'm saying this is not factorable, but then the truth is it's not factorable with real numbers. There's some i's involved. So since we can't factor anymore, we use our zero product rule. We set each of these things equal to 0. So we set x minus 2 equal to 0, and we set x squared plus 4 equal to 0. And these are independent. Add 2 to both sides, you get x, I was about to say x squared on accident because I'm looking at the next thing, x equals positive 2, and that is one of the zeros. Then we have x squared plus 4 equals 0. Now again, that's not factorable, so because we just have an x squared and no other x term, we can use that square root property where we kick the 4 to the other side. So that would give us x squared equals negative 4 because we subtract 4 on both sides. And then we do not just take a square root of both sides. That would be wrong. So I'm wrong for now, I'm wrong for now, I'm wrong for now. This is wrong. Why is it wrong? Because we take a plus or minus square root. I've told you it's never going away. I don't lie to my students. And I just hit save on accident. Not that it matters. That was just the pause. Now, the square root of negative 4. Oh, the negative, we can't do that. Yes, we can. Pull out an I. Square root of 4 is 2, so that's just x equals plus or minus 2i. So our zeros are 2 and plus or minus 2i. And you could write that as 2 comma 2i comma negative 2i if you want to write them separately. But this is good enough. These are x values where our graph would cross. Again, these are x values, and I should have written x equals now. Why didn't I? I thought I said it. It's fine, but I would much rather see the x equals 2 comma plus or minus 2i. So again, these are where the graph crosses the x-axis. Why? Because these are x-intercepts. Why? Because we set the function or the y value to 0. Now, this one right here, these are imaginary numbers, which means it doesn't actually cross there. It only has one point at which it crosses the x-axis. That's going to happen sometimes. But that fact that you have these intercepts at 2i and negative 2i can still be important for the function. It still has consequences. Maybe just not consequences we get in, except for the fact that it's not an actual crossing point. So what's kind of important for us to understand, and is ultimately important later, is that the leading exponent was a 3, and we found 1, 2, 3 unique solutions here. We found 3 solutions. That's pretty consistent. The exponent tells you how many solutions you generally have, but not necessarily how many unique solutions. I could have a solution repeated multiple times. I could have x equals 2 work 3 or 4 or 5 times. But since this is an x cubed, the most number of solutions I could have is 3. That's a much better statement. And in fact, that's known as the fundamental rule of, the fundamental theorem of algebra, that the leading term's exponent is the most number of zeros you can have. That's something that's studied a little more heavily in some pre-calculus classes, but not ours. We just kind of stick to this side of things. But if I had found, say, 5 solutions, I would know that's wrong because this says I found too many solutions. All right, B. F of x equals x to the 5th minus 20 x to the 3rd. All right, so we're only focused on finding the zeros here. Ultimately, we will do all of this stuff together, but for now, one thing at a time. So we're just setting the function equal to 0. 0 equals x to the 5th minus 20x cubed. Remember, this is equivalent to the y value, which is the height being 0, which is why they're the x-intercepts. Then we factor. This is a binomial, but it's not one of those special formulas. It just has a GCF in it. Between x to the fifth and x to the third, we can take out 3 of them. So we take out x to the third. X to the fifth divided by x third is x squared minus 20, and the x to the third is just gone. X squared minus 20. You can technically factor this as a difference of squares, but not using whole numbers, because we don't know the square root of 20 specifically. So we're going to go and do it the same way we did as the last time. All right, but we can go ahead and use our zero product rule. And we set the x cubed equal to 0, and then we set the x squared minus 20 equal to 0. Well, if x cubed equals 0, that means we just take the cube root of both sides. Not a plus or minus. Not a plus or minus, because that exponent is odd, not even. And that tells us just x equals 0. There's an awesome fact here. Even if you did a plus or minus 0 is still 0. Here's the awesome fact. This 3 right here has absolutely no effect on the actual 0 itself. If that 3 had not been there, we would have gotten the same solution. If this was a 2, we'd get the same solution. If it was a 17, we'd get the same solution. If it was a 45, we would get the same solution. When you have just an x to a power set equal to 0, the exponent has no effect on the solution, except for the multiplicity, which we haven't talked about yet. All right, add 20 to both sides. You get x squared equals 20. Take the square root of both sides, right? So x squared equals 20. A little more room for my square root. All right, so we just take the square root, right, Mr. Beckner, right? Question mark, inflection in voice? No, plus or minus square root. Don't forget your plus or minus when it's necessary. It will always haunt you for the rest of your mathematical careers. Let me just kind of go over here. The square root of 20 we already said we don't know, which is the whole reason we were doing this. Otherwise, I would have factored it as a difference of squares. But we can write 20 as 4 times 5. So that's plus or minus the square root of 4 times 5. And we do that because we know the square root of 4. Remember, only try and break this up as a product where you know one of the square roots. I don't do 2 times 10 because I don't know either of those square roots. Square root of 4 is 2. So that's plus or minus 2 square root of 5, meaning that our zeros all combined together are x equals 0, and then plus or minus 2 square root of 5. So those are the locations where your graph crosses the x-axis. Now this is 3 actual crossing points. You would want your calculator to estimate 2 square root of 5. We did a problem like that last time. But remember, for test 3, you are allowed a calculator. Test 2, you are not. Do not use calculators on test 2. There are ways I can tell, and I'm not going to spoil those ways. I mean, obviously, one of them can be showing your work, but there's other ways past that. So this had a leading exponent of 5, and we found 3 zeros. But you might go, well, aren't we supposed to have 5? No. We can have 5 zeros, but not necessarily 5 unique zeros. In fact, because this exponent was a 3, that relates to that thing I keep kind of previewing about multiplicity. It means that 0 happens more than once. It actually happens 3 different times, because that's 3 different x's set equal to 0. X cubed is like having x times x times x equals 0. And then 0 product rule, you're just setting each of these equal to 0 3 at a time. So that x equals 0 happens 3 times. I should have just hit the eraser. That's bad, my bad. All right, there we go. So now that we've kind of got something connecting that dot, we can talk about our multiplicities finally. And no, not that silly movie from the 90s, which maybe most of you don't even know about. Because that was a long time ago now, isn't it? The multiplicity of zeros. I think I have a note there that's repeated. If a 0 is repeated, and that was an unintended pun, if a 0 is repeated more than once, it has a multiplicity greater than 1. So the multiplicity is the number of times a 0 occurs. It relates directly to an exponent, as I was just talking about. So if a 0 is repeated more than once, it has a multiplicity greater than 1. If the multiplicity of the polynomial 0 is odd, this odd and even thing's coming back into play, and this is not just the exponent of the entire thing, but it does relate to an exponent. So if the multiplicity of the polynomial 0 is odd, then the function will cross the x-axis at that point. But if instead the multiplicity is even, then the function will bounce on the x-axis at that point. What the heck do I mean by bouncing and crossing? Again, this is the thing I mentioned that's kind of a repeat. Didn't mean to have it there twice. That's okay. What is bouncing? What is crossing? Where does this multiplicity come from? Well, let's write that out directly, that the multiplicity exponent when you're setting individual factors equal to 0. It's not the exponent of the leading term, it's the exponent of the x's or the parentheses when you're setting each thing equal to 0, when you're using that 0 product rule. That's when you can tell your multiplicities. So once again, what is bouncing? What is crossing? That was a really wide axis. This is what it looks like to cross. This is the only point I'm actually talking about. That is crossing the x-axis. Because we went from below to above or vice versa. So if you had a graph that did this, this would also be crossing, but I don't want to leave that up there. It doesn't matter whether you're going down, up, or up to down, it's just doing one or the other. Crossing means you go from the bottom to the top, or the top to the bottom. I just crossed a couple of words there, didn't I? So what's a bounce look like then? A bounce looks like, and it doesn't matter which side of the x-axis it's on. Go. Oh, jeez. Sorry, real life thing just happened. This right here is, again, your point where you're touching the x-axis, but instead of crossing, it looks like the x-axis was a floor. It looks like this was a ball that we threw on the floor, and then it bounced back up. Oh, geez. Now I'm being terrible with my pen. I know I'm not great in general, but I'm distracted. That is a bounce. So bouncing makes the x-axis look like a floor or maybe even a ceiling. Again, it could look like this. That would also be a bounce. So it crosses when the x-axis is, well, not like a floor, it's just going to keep on trucking, and it bounces when it's like a floor or a ceiling. What does this relate to? It relates to the exponents being even or odd. You know why it relates to that? Because check this out. Here are our graphs. Here's our graph of x squared. Poorly drawn. Ugh. One more try. Much better. Minus that arrow. There we go. Look right here. It crosses, I'm sorry, it touches the x-axis right here, and that's a bounce. And that was the graph of x squared, which has an even exponent. Here's the graph of x cubed, which at its singular x-intercept, look what it does. It crosses. And look at what the exponent for that is. It's odd. So once again, you can just blatantly memorize sentences and if this then that, if this then that kind of things, and that's fine. Or you can relate it to a basic graph that I've told you to memorize. But you have to have your ducks in a row. I know I love that phrase. So this x squared graph not only gives you n behaviors just by looking at what the arrows do, it tells you what your even exponented zeros, what they do. They bounce just based on that shape. Same thing for x cubed. It gives you n behaviors. And if you make it negative, they switch directions. And at its singular x-intercept, it crosses. So same idea. So these two graphs, as well as their reflections vertically, give you n behaviors and multiplicities of zeros bouncing or crossing. Extremely helpful, extremely helpful. So let us moving some stuff. Try this out for example 3. Determine the n, sorry, not, I keep wanting to say n behavior, the behavior at each zero. 0 means intercept, x-intercept specifically. A will have f of x equals x plus 3 squared times x minus 5 times x, that got ugly, plus 4 squared. So that's our function. I'm not asking for the n behavior this time. Again, by the end of this section, we will start doing all of that stuff. The n behavior, the zeros, some other stuff as well. It'll be good. But all I'm asking for is the behavior at each zero, whether it bounces or whether it crosses. So I want you to find the zeros. I want you to describe the multiplicities. Then I want you to describe whether it crosses or bounces. To do any of this, though, we have to set the function equal to 0. Now, you might have been slightly annoyed because this was factored, and like, oh, well, the n behavior is more annoying because I got to figure that out. I don't know what the leading term is. True, but the fact that this is already factored makes it much easier to find the zeros. This problem, if I had given it to you in the expanded format, which would have been like x to the 5th, oh, geez, I don't even know, minus 48 x to the 4th. I don't know. I can't do that in my head that quick. And that's telling you something. And the rest of it takes even longer than the x to the 4th term. So thankfully, we don't have to multiply all this out. That would be terrible. We don't have to have factored something of that form. That would have been terrible. You wouldn't have known how to do it, in fact. At least that's my assumption. And if you do, then prove me wrong. But all we got to do is just do the zero product rule, and we set the x plus 3 squared equal to 0. We set the x minus 5 equal to 0, and the x plus 4 squared equal to 0. Now, I've already talked about how these exponents, when something is set equal to 0, these exponents don't matter. When you take each of these square roots, the plus or minus square root of 0 is 0, so the exponents don't matter for the solution. Just the number, they matter for the multiplicity. So having x plus 3 squared equals 0, you take the plus or minus square root of both sides, you get x plus 3 equals 0. Subtract 3 on both sides, and you get x equals negative 3. For the middle one, it doesn't have any exponents, so just add 5 to both sides, you get x equals 5. For the right one, if you want to show your work of taking the plus or minus square root of 0, you'll just get straight to x plus 4 equals 0. Subtract 4 on both sides, and you get x equals negative 4. The even or oddness of these numbers does not matter. It does not matter. It does not matter. These are the actual zeros. Excuse me. What matters is the even or oddness of the exponents of them. Now, I didn't have an exponent written for this middle one, which means it was a 1, but nobody ever writes that, so I keep it unwritten. I'm just reminding you that an unwritten exponent is a 1. So I'm going to write m equals to represent the multiplicities here. The multiplicity is, again, literally the exponent before you got rid of it. This was a 2, so the multiplicity is a 2. This had a 1 implied there, so that's a 1. This also had an exponent of a 2. This is the thing that matters whether it's even or odd. This m is even, this one is odd, this is even. What happens at these evens and odds? That tells us whether we bounce or we cross. Please ignore the typing up there. Oh, I'm gonna have to do this. If it's even, that means it relates to the x squared graph. Okay, so I'm not even gonna pull back up to the text and stuff, just this. It relates to the x squared graph, and x squared, it does this on its x-intercept, which is a bounce. So that means at that point on the graph, it would bounce. And that detail, believe it or not, is almost everything we need just to paint the picture, to get a good sketch. With this one being an odd, that means it relates mostly to an x cubed, which means they go in opposite directions, which forces the crossing to happen. Again, odd exponents relate to the x cubed graph, or you could even say it just relates to an x to the first graph, which would look like that, or the other way, depending on the sign. Either way, those intercepts would cross. And then this last one is even, so that is also a bounce. Again, the even and oddness had nothing to do with the x values. When I was talking about the bouncing and the crossing, it had nothing to do with the x values. It had to do with their exponents. Oh, come on. If I do this, will it work? Please. Sweet. Sometimes you can trick the system. So again, the grand scheme of things, graphing this polynomial is what we're going to be doing. We might get to one today. But this is one of the steps we need. We also would need its end behavior. We need its end behavior, and we need the behavior at each of the zeros. That is practically all we need, surprisingly. All right, B, let's do f of x equals, and let's do another one that's factored, 2x to the 5th. They won't always be factored, don't worry. I'll give you one that's not. Times x plus 9 to the 7th, times x minus 1 to the 4th. This would have been pure nightmare fuel to try and factor. I don't even think that I could have done it without the help of a computer. Now, you know what? Actually, I'm gonna take that statement back. I'm gonna take that statement back. I could have factored this. It would have taken me a very long time without some technology help, but I could have done it based on the size of these numbers. Now, if these had been wackier numbers, that's another story, but don't worry about what I'm saying for now. All right, we're finding the zeros and their multiplicities and saying whether they're bouncing or crossing. To do all that, set the function equal to 0. And in fact, I'll be teaching you the technique to factor this polynomial if it had been, is that 12, 16, so that's 2 times x to the 16th plus, and there's probably 16 full terms of that polynomial, maybe even 17. And then asking you to factor, and I'm telling you that it's factorable, and I'm teaching you a technique that it would work on. Yep, these are facts. Facts of factoring. All right, but we don't need the leading term. We're not going to expand this. We're not even going to pretend to expand it with the covering of the 9 and the minus 1. We just go straight to zero product rule. So 2x to the 5th equals 0, or x plus 9 to the 7th equals 0, and x minus 1 to the 4th equals 0. Some people don't even write the exponent parts there because they're irrelevant. Again, for this first one, you divide both sides by 2. And then you would get to it, but it still will be irrelevant because 0 divided by 2 is 0. So x to the 5th equals 0. Let's make a wall. Then taking the 5th root gives us x equals 0. Taking the 7th root gives us x plus 9 equals 0. Taking the 4th root, a plus or minus 4th root technically, tells us x minus 1 equals 0. Subtract 9, add 1, we get x equals -9, and x equals +1. 3 zeros. Now that was an x to the 16th problem, and yet there's only 3 zeros, which means they're repeated a heck of a lot. How heck of a lot repeated are they? How much are they repeated? The exponents for each factored form tells you that. Since this exponent was a 5, that means the multiplicity was a 5. Since this exponent was a 7, its multiplicity is 7. Since that exponent was a 4, its multiplicity is 4. That's the number of times it occurs. Now, all we care about now for the bouncing and crossing is the m's. I no longer care what these x values are temporarily, because we'd have to place them if we were graphing. Again, for now, all I'm worried about is the bouncing and crossing based on the even or oddness of this. 5 is odd, 7 is odd, 4 is even. The odds bounce and the evens cross, right? Question mark. So again, what you can do is, oh, well, let me relate this to the x squared and x cubed graphs. All right, x squared looks like this. That's a bounce. X cubed looks like this. That's a cross. Even, odd, boom. There you go. That's all you got to do. A picture's worth 1,000 words. Or if you like blatant memorization, you go back to the paragraph. If this, then that. If this, then that. All right, so odds, cross, evens, bounce. There we go. So again, you will be in situations where your polynomial is not already pre-factored for you and you'll have to factor. But I would not give you a situation where it's an x to the 16th. I'm talking about things like in the ballpark of x cubed, x to the 4th, or maybe even an x to the 5th. That's what I typically would be having you factor. Without telling you to factor, you have to know that factoring is part of the whole process. All right, end behavior. Talks about just the ends, whether they go up, down, or a mix. All based on the even and oddness of the leading term's exponent. Behavior at the zeros is based on the even or oddness of the zero's exponent. There's such amount of similarity here, such a good amount of similarity here, which means if you only practice this once or twice, you're bound to mix these things up and make mistakes, which is why we ask you, even though there may only be like 5 homework problems or something, do them over and over and over. Go to the internet and find more problems. Go to your textbook and find more problems. I am a strong believer that the amount of homework in my math lab is not enough for most students. But I'm not allowed to add problems. And my lazy students would hate me if I did, but unfortunately, the brains would be better off for it. Okay, actually I didn't want to hit enter. I want this up here now. All right, the last thing we'll talk about before putting all this together, and admittedly, this isn't something you have to do, this turning point thing, but it is very helpful as a self-check, kind of like talking about whether the quadratics pointed up or down. Even though that happened automatically throughout the problem, it was just a good self-check. Because if we said it should point up and then we make a graph that points down, something squirrely. Turning points. If a polynomial has a degree of n, then it can have at most n minus 1 turning points. What that means is 1 less. So if your polynomial's degree is 7, which means the leading term has a degree of 7, that means you can have 6 turning points. If your degree is 10, you can have 9 turning points. If your degree is 2, you can only have 1 turning point. Notice we're using the word can, not will. What exactly is a turning point? A turning point ends up being a local max or a local min, and here's what they look like. So here's a graph. Your turning points are where you change from increasing to decreasing or vice versa. Those are our TPs, our turning points. It's where you turn from going up to down. You go from making money to losing money, that kind of thing, or vice versa. Your functions don't have to both point down or point up to talk about turning points. It's just they are maxes or mins. They're where you change from going up to going down or going down to going up. So because there are 3 turning points here, that means this polynomial could not have been just an x squared or just an x cubed. It would have had to have at least been an x to the fourth. So how is this useful? Because you're going to be painting pictures that look essentially like this. They're not going to be very exact. You're not going to be plotting 30 or 40 points. You're going to be plotting not even these points specifically, and that's more of a calculus concept, plotting the turning points. We just kind of guess where they are. We end up plotting, and I'll do in red what we would be plotting. We'd be finding the intercepts like so. We'd be using the end behavior to kind of match things up, and then boom, there's our graph. It's not going to be intensely accurate. It's going to be more of a sketch, but it's going to be a really, really, really good sketch. So what this does for us is, let's say that we made a graph with 3 turning points, but the function was x to the third plus blah, 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 blah. There was no x to the fourth or higher. So that would say, well, we goofed because our graph has an extra turning point. That means we probably need to start from scratch or try and find the mistake. Last but not least, this is something I don't use a lot of, but I will mention it once or twice when it's relevant. You can certainly use symmetry to get a better picture of the graph. And remember, the only symmetry with functions is either with respect to the y-axis, which means left and right mirror each other like an x squared or x to the fourth graph, or to the origin, where you're going across both x and y-axis, which is like the x cubed graph. So that's beneficial when you plot the right half of a graph, you know it's even, you know that it's symmetric to the y-axis, in other words, so you can just flip it over and boom, you're done. You don't have to paint the rest of the picture. But that requires you testing the function to be even or odd, which is time consuming, and most functions are not even or odd, so you usually end up wasting time unless you just know, hey, I know, I've gotten used to, and when I see this thing, that's probably even. When I see that thing, it's probably odd. So that way, if you see something that doesn't really give you those clues, don't even bother testing it. And as I've mentioned, those clues deal with whether the primary exponents are even or odd. But constant terms can throw you off. And they don't have to just be exponential terms, but it wouldn't be relevant for this section. All right. Finally, let's put everything together. We're going to do the end behavior. We're going to do the zero behavior, which is the multiplicities. We're going to do the other intercepts as well, and maybe symmetry if you feel like it's necessary. So to graph any polynomial, this is true for any and every polynomial, a good way to get a solid sketch. Use your leading coefficient test to determine the end behavior. We practiced that 3 times. Find your zeros, which is also known as your X-intercepts, by setting the function equal to 0 and identify the multiplicities. Now, when I say identify the multiplicities, ultimately I mean tell whether you're going to bounce or cross at that 0. Then find the y-intercept, because it's pretty easy to find generally, and an extra point that's easy to find is almost always helpful. Steps 4 and 5, I will admit, you don't have to do. You don't have to use symmetry. You don't have to check that you don't have too many turning points. But it's probably a good idea, because you might find yourself making a random mistake or two, and step 4 could have prevented the mistake. Leading coefficient test, which deals with the even and oddness of the leading terms exponent. Find your zeros and identify the multiplicities, which has to do with the even and oddness of the zeros exponents. Find the y-intercept, which is just f of 0 as a reminder. So that's just plugging in x equals 0. And then make sure you don't have too many turning points. You can use symmetry if you want. You can plot additional points if you want. You can find f of 1, f of 5, f of -3. But that's not really the idea behind here. And when you're taking your test on this stuff, if a student tries to show their work and all their work is just f of 0, f of 1, f of 2, f of 3, f of 4, they're not showing that they understand a concept, then I'm not going to give them partial credit. I might not give them any credit. So please make sure that you understand the expectations. And I might say, well, Mr. Beckner, why wouldn't you just take graphing of doing f of 0, f of 1, f of 2, f of 3? Because I can give you a graph where doing those values will be completely irrelevant to the primary section of the graph we're looking at. Maybe you need to go into f of 1,000 and 1,002 and 1,009 and 1,040, something like that. I shouldn't be saying and there, but it's fine. Ands are only used for decimals and technical. technical levels. All right, so drum roll. Let's finally put all these pieces of the puzzle together. So weird sometimes. Example 4. Sketch polynomial. And it might say graph. I prefer using the word sketch because it implies that some of these are not super detailed. And for A, we're going to have f of x equals x to the 4th minus 2x squared plus 1. We got 15 minutes. All right. So the first thing I like to do is the end behavior, which the end behavior says only look at the leading term, which is not necessarily the first term, but it is this time. So that's an x to the 4th, which 4 is even. So it's got an even exponent and a positive coefficient, which means the end behavior, this is the world's tiniest graph, while we have no clue what happens in the middle, we know because it is an x to the, it's an even exponent and a positive coefficient, we should know with practice that both ends go up, because that would relate to the positive x squared graph. And again, positive x squared looks like this. We just cut out the middleman. Now, when I go to make my actual graph a few steps later, I'm not going to have this taking up the majority of the section. So here's the graph. What I'll do is I'll just put vertical arrows on the far ends, just kind of as checking points. These are basically a comment to myself of where to come from and where I should end up going, but not yet. So we got our end behavior. That was the leading coefficient test. Next, we're up to step 2. Find the x-intercepts by setting the function equal to 0, and then identify the multiplicities and balancing of the crossing. So for the second step, we set the function equal to 0. So we go 0 equals x to the 4th minus 2x squared plus 1. Now, some of you may know how to factor this immediately, and it is factorable, but, and what I mean is by using like an x squared in the first spot of each instead of an x, but we practice this substitution concept. So this is where we say, let u equal x squared, because these two things, one is double the other in terms of an exponent, which means it's in quadratic form. We practiced that in chapter 2. So we said let u equal x squared, which makes u squared x to the 4th. So now we have 0 equals x squared, not x squared, excuse me, u squared minus 2u plus 1. This is a change of variables. Again, if you're rusty on this, go back to where we were solving equations. Actually, that was chapter 1. That was chapter 1, maybe 1.4, 1.5. All right, this is pretty easy to factor. It's we don't need to do the AC method or trial and error because the leading coefficient's a 1. We can just go 0 equals u and u in the parentheses. In fact, I'm gonna, yeah, I wanna do it this way because I might need this space. So u number, factor pairs of 1 are just 1 and 1. So those are literally the only options. And to make sure your factors add to -2, they both need to be -1. And if you FOIL that, it does turn out to be okay. But now we go back to x. Now that we have this factored, and you could solve this for u and get u equals 1 and u equals 1, but for now, for us at this point in our career, it's actually better just to go ahead back to x's. So we get 0 equals x squared minus 1 times x squared minus 1. Now, some people will say, well, that's the same thing, so let me just write this as x squared minus 1 squared, and you can, but it's a bad idea. It's a bad idea because your multiplicities might become hidden. So I know this is going to seem weird, but I'm going to factor this more. Instead of just saying, since I have a repeated thing, let me do that as x squared minus 1 all squared. Let's factor it more because each of these is a difference of squares. So x squared minus 1, this first one, is x, why did I do a double parentheses? X plus 1 times x minus 1. That was this, but the other one is literally the same thing, so I'm going to literally see the same thing twice. X plus 1 times x minus 1. Now, this is where you're going to go, oh, you're a hypocrite. Because I said, don't squeeze these together and make it the same thing squared. Now I'm going to, only now do you combine the common ones, this x plus 1 and x plus 1. So that's x plus 1 squared. Then the x minus 1 and the x minus 1 makes an x minus 1 squared. See, you don't want to do it this way. I'm going to erase this after a minute, because the x squared minus 1 times x squared minus 1 equals x squared minus 1 squared. So now you've got double exponents. When you set that thing equal to 0, somebody is going to mess that up. I would say most people are probably going to mess that up. So that's why that's a bad idea. We like what we call linear factors inside. It's just an x plus 1 or 2x minus 3, something like that. Now we do our zero product rule. So we set x plus 1 squared equal to 0 and x minus 1 squared equal to 0. Now, admittedly, that particular issue I'm having in this problem is not super common, but you could see it homework or tests, which is why I'm doing it. I want to make sure you see this weirder problem. We've said the exponents don't matter for actually finding this. That is the same thing as saying x plus 1 equals 0, because the square root of 0 is the same thing. Oops, no parentheses necessary. So you get x minus 1 equals 0. Subtract 1 on both sides, add 1 on both sides, you get x equals negative 1 and x equals positive 1. Those are our zeros. Those are the zeros. Those are the x values of the x-intercepts. Remember, the y values are 0 because we forced it to be 0. But we also want to talk about their multiplicities. That dealt with their exponents, those 2's, which again, you might not have gotten correct the other way around. You might not. And also, you'd end up doing that plus or minus square root case that you could mess up. This is just a lot easier to get right. So these both of these multiplicities were 2 because both of their exponents were 2. And those are even, which means they bounce, not cross. Next up, we want to do the y-intercept. Let me just do that over here. Y-intercept, which is f of 0. So f of 0 equals, well, this was the original function right here. I know I have that equals 0 part, but if you just scroll up a little, you can see it without that. This was the original function. Just turn the x's into 0. So that's 0 to the 4th minus 2 times 0 squared plus 1, which is very obviously 1. So f of 0 is equal to 1. So we have a whole bunch of points now. We have negative 1 comma 0, and we have positive 1 comma 0, and we have 0 comma 1. The first two were the x-intercepts we found over here. The third one is the y-intercept we just found on the right. We have the end behavior that both ends go up. We have our 3 points. We know at 2 points, the bouncing or the crossing aspect. There is no bouncing or crossing on y-intercepts. Y-intercepts will always cross. You can't bounce. If you wanted to bounce, this is what a bounce on a y-intercept would look like. All right, we're coming in. This would be a bounce. And now it's not a function because it fails the vertical line test. All right, so let's make a nice big graph. We don't need to label a whole bunch of numbers up here, it looks like. But I will go at least to 3 in each direction. 1, 2, 3. 1, 2, 3. 1, 2, 3, 1, 2, -3. So for the end behavior, we said both ends go up. So I just put some arrows on the side of this graph, not actually on the graph, showing that both ends go up. And I don't curl them. I could, but I mean, I certainly could. It wouldn't be any different. It just might mislead you that they're going to be coming in not as hot. Then we plot our points, which were the -1, 0, which is right here, the +1, 0, and then the 0, 1. Almost looks like a little triangle. That is not the graph. You might think it's, oh, it's just a quadratic, so it looks like this. Nope, that is definitely not the graph. Why is this not the graph? It doesn't match the end behavior. That's completely wrong, so that couldn't be it. But I'm going to make this graph with only these 3 points, the graph of some super complicated polynomial with other bends and twists and stuff. We are going to bounce at both of these points. So that thing I just did, that would have been crossing. This would be crossing through those points, which is very obviously not the case. Now, what you want to do is start from the far left and just come from this section and just try and hit the first point on the left, and then bounce across, and then hit the next point, and then hit the next point, and then bounce across, and then hopefully you're matching the end behavior here. So I'm going to start from the upper left, and I could start all the way out here, but these things tend to be pretty steep. So I'm going to go a little closer and do something more like this. So that's what I believe the left side looks like, just based on the end behavior and then having to touch this point. Now, if you think it does this, that would be crossing, which is wrong. Now, I'm not talking about the fact that I made a line here. Even if you do this a little more steep, that's still wrong because you crossed. We are supposed to bounce. So we turn around. So bouncing is also a turning point, which is also a local max or min. Now you might say, okay, we'll just keep going up. Well, no, use those next points to kind of predict your path. This next point is here, so I'm going to say we're probably going to do something like this. Now you might say, well, Mr. Beckner, why aren't you going to keep going up? Because I got to now hit this point, so it's got to turn around. And now in theory, it might go up some more and eventually turn around. It's usually not the case. So we like to kind of assume that the halfway point between them is that kind of local max or min. Again, not always the case. I did that a little too sharp on this side. And that's not something I would grade on. But we're usually having nice smooth turns, something like that. And then at this point, we were also supposed to bounce. So we do not do this. That would be crossing. We bounce, so we go back up. You might say, okay, well, how do I know what to do from here? There's no more points. Because there's no more points here, 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 or here, that's telling us we don't have to hit them specifically. We just keep on trucking in the path we have right here. Just keep going, keep going, keep going, keep going. Forever and ever and ever. And look at that, it matches the right end behavior. So we started based on what the left end behavior is assumed, and then if we bounce and cross and hit all the points properly, the other end behavior should match. This is a very well done sketch of the function x to the fourth minus 2x squared plus 1. And if you don't trust me, which I know most of you don't right now, you could pull out a graphing calculator to confirm your results. X to the fourth minus 2x squared plus 1. And you hit your graph button. I just made sure I was in a standard zoom, and look how good that looks. That is freaking good, isn't it? I even predicted this correctly because it was a halfway point. I will give you a graph where it's not a halfway point, and I'll talk about why that weird issue is a thing. But for now, that is going to be time. So we're going to call it a day. We will do several more of these examples next time because I know this is a lot all at once. But again, a lot of the basis of this is just taking old stuff we've already done, like factoring and finding zeros, and then looking at some even and oddness of exponents, different exponents. So we have to keep everything straight, which one deals with the bouncing or crossing and which one deals with the end behavior. Intercepts, which we were already practicing back in the quadratic section. And then just kind of going with the flow, bending and curling and hitting points, paying attention to the bouncing and crossing, and then making sure end behaviors line up. So on that note, Oh, I need to mention, it's possible that on Wednesday I will not be able to teach live. I've got this whole contracting situation going on at my house right now, and
Hit a button wrong. Sorry about that. Okay, so as I was saying on that note, we're going to go ahead and call it a day. So we did finish 3.2 like I promised, so that will be due in a week, assuming my math lab starts behaving regularly. Again, it seems fine this morning so far, but it also seemed fine the other night, and then it went back to being weird. So I'm not going to count my chickens before they hatch, as they say. But again, just whenever you notice that it's working and you can get to work on your homework, please do so to catch up, because I'm not going to keep extending these and extending these once it is working regularly. So hopefully this will be the last case, but just look out for any emails from me, or shoot me in the email if you notice any changes to the weirdness. Besides that, have a good weekend, take that test if you haven't, and we will see you next week.